Okay, we're in chapter 4 now, and chapter 4 is the first time we really start taking a hard look at higher order differential equations. Even though we've defined these things before, the last couple of chapters have been spent really just looking at first order equations. And that's good. You know, we came up with several techniques for dealing with those, looked at applications of those, but those techniques that we talked about in general are not really going to be that helpful when we're dealing with something higher than a first order equation. So we need to start developing techniques for these higher order equations. And this first section that we're going to cover, I'm going to just give you a disclaimer on it. There is a whole lot of information that I'm going to throw at you in just this first section. And none of it is actually going to give us a technique for explicitly solving a second, third, fourth, or whatever higher order differential equation. As the name of the section implies, we're dealing with theory here. And what this is doing is it's sort of laying some groundwork that's going to give us tools that we can use when we actually do start solving these higher order equations a little later on. It's really important to lay this groundwork first before we just jump in to solution methods, because otherwise none of that stuff is really going to make much sense. I'm going to add to my disclaimer here that you will benefit a huge amount if you have had linear algebra already as we go through this section. Even though linear algebra is not a prerequisite for this course, it is all over the place in this specific section. We're going to talk about linear combinations. We're going to talk about determinants. We're going to talk about linear independence and linear dependence. And we're going to talk about linear operators, all in this one section. Those are all linear algebra topics. You have most likely heard of determinants before this class. You usually learn those, in a pre-calculus class, or even sometimes algebra 2. If you've had calculus 3, you've definitely seen a determinant when you define the cross product. So I'm going to assume that you know how to evaluate a determinant here, but I'm not going to assume that you know any of those other things I talked about: linear operators, linear independence, that kind of stuff. Now, I will give you an explanation of those topics, but because, again, this is not a linear algebra course, it's going to be a somewhat rushed explanation because we have to do it that way. So that's kind of what I mean. If you've already heard of a lot of those things from linear algebra, you're going to understand this section a lot better than somebody who has not. I'm just giving you that heads up. But I'm 3 minutes into this video and I haven't really done anything yet. Let's go ahead and start. So Our focus is not just on higher order equations in this first section here. We're focusing specifically on linear equations, nth order linear equations this time. Okay, so here's your general nth order linear equation. We've already defined this. And this one I'm actually giving you an IVP. So we're looking at this nth order linear differential equation, and we have initial conditions. And remember, if it's nth order, then you have to have n initial conditions. Y of x naught equals y naught, y prime of x naught equals y naught, and so on and so forth. And so far, because we've only been dealing with first order equations, our IVPs have only had one initial condition, right? So it's easy to forget this until you get to this chapter, but when you have multiple initial conditions like this, the input needs to be the same number in each one of these. X naught is showing up in each one, right? Even though the outputs all potentially look different. So right away, we have a theorem here. And one thing I actually meant to add to my disclaimer as well, because of how much the material in this chapter, in this section in particular, hinges on linear algebra, we're going to state a bunch of theorems, and we're not going to prove them all. In fact, I think I only prove a couple of them. And the reason for that is because an adequate proof of those theorems requires much more background knowledge in linear algebra and some other stuff that we just don't have the time to get into. So there's going to be a lot of me saying, here's a theorem, trust it, without me actually proving it to you. This is the first of one of those theorems. So we're looking at this dE up here, and we're going to say, let's suppose that all of these coefficient functions, an minus 1, all of them up here, and as well as this function on the right-hand side, g of x. Let's suppose they are all continuous on an interval I, and in particular, we're going to assume that we can call this a leading coefficient, the an of x, the first function of x right there, is not equal to 0 for all of the x's in that interval. Okay, so I'm not just saying that it's not the 0 function. I'm saying that it's not equal to x for anything that I can plug in there from that interval I. Now, if x equals x naught is some point within that interval, then a solution to this initial value problem that we stated up here is guaranteed to exist, and not only that, it's guaranteed to be unique. Those are two very, very strong and useful things that we can say about this kind of a DE. And again, I'm not going to prove this. We're just taking that fact for granted here. So here's an example right away where we're going to use this. I would like to solve this DE, 5y double prime minus xy prime plus 4x squared y equals 0. And here are my initial conditions. Notice it's a second order equation. So I have a total of, actually, did I need all of these? No. I think I have too many initial conditions here. Sorry, we don't really need this last one. I'm going to eliminate that because we only need to go to the n minus 1th derivative, which is our first derivative. So that's more information than we need. But we have this DE. Here's my initial conditions. Y of 2 equals 0. Y prime of 2 equals 0. Now, normally it wouldn't make sense for me to put a problem like this in this section because we haven't talked about any techniques for solving second order equations, which is what this is. But this is one that if you think about it for a little bit, you might be able to solve it by inspection. You are asked to do that a little bit in the problems in this section. And when we solve something by inspection, oftentimes what you should do is try the simplest possible solutions, namely constant solutions. And a good thing to check first is the trivial solution. Remember, the trivial solution is the constant function y equals 0. Notice if I put if I check the solution y equals 0, the constant function 0 is its own derivative and its own second derivative. It's its own nth derivative, right? So I have y equals 0, y prime equals 0, y double prime equals 0. Everything on this left-hand side is equal to 0, and 0 equals 0, right? So that is one solution to the differential equation here. Remember, a differential equation can have infinitely many solutions until we impose some initial conditions on it. So does that particular solution that I picked out there also satisfy these initial conditions? Well, yes, it does, because it wouldn't matter what I plugged in for my constant function 0. If y is equal to 0 and y prime is equal to 0, then of course y of 2 equals 0 and y prime of 2 equals 0. So y equals 0 is a function that satisfies this DE and these initial conditions. What this theorem says is that because I have found a solution to this, then I can say that it is the solution, because it's saying that any solution to an IVP of this type is guaranteed to be unique. There is only going to be one. So if I find it, I know that I don't have to look anymore. Okay? Next up, I'm going to give a definition of what we call a boundary value problem. We do not deal with these much at all in this class. But there are other techniques that we could develop for dealing with boundary value problems. There's entire books dedicated to just this type of problem. A boundary value problem initially is going to look like an IVP, but there's an important distinction. So first of all, we only talk about boundary value problems, or BVPs for short, for second order or higher equations. And what makes a boundary value problem different from an initial value problem, you still have a DE that you're working with. In this case, we're looking at a second order linear DE, but it doesn't have to be considered a boundary value problem. Down here, where I would normally see initial conditions, we see something slightly different. Y of A equals Y naught, Y of B equals Y1. The important difference that's happening here, which you don't see in an initial value problem, is that these inputs are different. I'm assuming A is not equal to B here. Whereas in an initial value problem, all of those inputs, those x naughts up there, are the same number. The reason these are sometimes called boundary value problems is usually what's happening is your solution, as always, is defined on an interval. And in the event that it's a closed interval, these values A and B are oftentimes selected to be the endpoints of that interval. So they kind of represent the boundaries of that interval. They don't have to be, but that's a common enough occurrence. One other thing worth mentioning, these don't have to both of these boundary conditions, which is what we call these, they don't have to just have y's. You can have y primes, so you can say y prime of A equals y naught, y prime of B equals y1. You can have a y here and a y prime here. Any combination of those is fine. What makes it a boundary value problem is that the inputs are different, okay? Boundary value problems, the only reason we kind of talk about these in this little section right here is to show that even though the DE looks essentially the same here as it does up here, just in the second order case, this theorem falls apart when we look at boundary value problems versus initial value problems. So here's an example. We have a two-parameter family, y equals c1x squared plus c2x to the fourth plus 3, which happens to be a solution to this DE right here. You can check this. I'm not going to go through the steps to check it, but I encourage you to, just for the sake of practice, show that this thing is in fact a family of solutions for this. We want to determine whether or not a member of this family satisfies these boundary conditions. Okay. Now this is a linear second order DE. So it fits the type of DE that shows up in our theorem, but these are boundary conditions, not initial conditions, because I have different inputs showing up here. So what am I doing to see if this works or not? I'm going to take, because I have a solution for y here, and I have boundary conditions which use y, I can plug these boundary conditions into this and try and solve for the parameters c1 and c2. Notice if I plug a negative 1 in for my x's here, I'm squaring it so it comes to 1, and I get c1 plus c2 plus 3 equals y, where y is equal to 0. So I have c1 plus c2 plus 3 equals 0 for my first boundary condition. If I plug the second boundary condition in, I'm plugging a positive 1 in, but if you notice the same thing happens, I'm squaring or raising to a fourth power, and I still get c1 plus c2 plus 3 equals, what is it in this case, 4, okay? Now if I were to take this second equation and subtract the first equation from it, I'm going to get 0 on this side because both expressions are identical, but 4 on this side. That's a contradiction. Okay? What that means is that this system of equations has no solution, which, taking that back one step further, means there are no parameters that I could plug into this family of solution that satisfies this. So there are... this does not satisfy these boundary conditions. So I would say no solution in that family. Okay? So you don't have that issue with IVPs, but it turns up with BVPs. And that's, I think, all that we're going to talk about regarding boundary value problems for the rest of this section. So let's continue onwards. Now, we're going to start throwing a lot of terminology your way, and some of this terminology is going to be terms we've used in a different context before, so I need to make sure you're making the distinction. So let's suppose that we're dealing with a linear nth order differential equation, and this is, again, that general form for that right here. Okay? We say that this equation is homogeneous if g of x, this function here, is 0. Okay, so if I have this expression on the left equals 0, that makes that a homogeneous DE. Now, that's different from the type of homogeneous equations we looked at back in or homogeneous functions back in section 2.5. So make sure you're understanding the difference between a homogeneous function and a homogeneous equation. They're not related, really. They're two very different things. If g of x in this expression or this equation appears anything other than 0, then we would say that this is a non-homogeneous equation. And your book takes section 4.1 and splits it into 3 sections. The first section is kind of brief, goes over the stuff that we just talked about. And then the second section talks about homogeneous equations. The third section talks about non-homogeneous. And as was the case back when we had another chapter that kind of split it up into subsections, I'm not going to use those labels. I'm not going to talk about 4.1.1, 4.1.2, and so on. I'm just going to call it all 4.1. But that's just to help you, if you're following along in your book also. So homogeneous if g of x is equal to 0, non-homogeneous otherwise. And if this is a non-homogeneous equation, then if we were to take a second equation that has the same left-hand side as our first equation, but 0 on the right instead of g of x, we call that the associated homogeneous equation to the non-homogeneous one. Okay, so if we have if we have a non-homogeneous equation, and then we take that g of x out and put a 0 there, now what you have is the associated homogeneous equation. We have to use that when we solve non-homogeneous equations of this type. Okay, now here's where we're going to start getting into some heavy linear algebra type stuff. Okay, so it's really, really helpful notationally to talk about this thing called the differential operator. Now, you don't use this much in a calculus class, this notation D, although oftentimes when you're first introduced to derivatives, they'll say this capital D is a notation that's sometimes used for a differential operator. And then in that class, you don't really see it much after that. This is where it shows up again. So you're more used to seeing this probably, d dx. If I put this next to a function, it says take the derivative of that function with respect to x. This differential operator d, we're going to use it kind of similar to how we use function notation, as you'll see in a little bit. But what we can do with differential operators is we can actually perform operations on them. And this gets into a weird territory where you may not be super comfortable. An operator, in more technical terms, is a type of function. And by performing operations on it, I'm talking about performing functions on functions. So functions that take other functions as inputs. That gets into, again, kind of more advanced territory. But we're going to hopefully clarify that with an example. So this, for terminology's sake, or for understanding the symbols, if I have d to a power of n, what that means is the nth derivative operator. And if I have some constant, that's supposed to be a capital D. If I have some constant times that differential operator d, then that means the same thing as this, a constant times the derivative with respect to x. So let me do an example where we define a differential operator and we evaluate a particular function using it. So here's a function that I want to work with, y equals x to the fifth. And I'm going to define the differential operator L equals d squared, which again, that's just the second derivative, minus 2d plus 8. What the heck does that mean? Well, it says I want to evaluate L of y. L of y is this. D minus 2d plus 8 of y. Now this looks like multiplication, but technically we think of it like function notation. Here's the name of my function, here's my input, okay? Now, evaluating this is going to feel like multiplication because it's going to look like I'm distributing this y in. But technically what this means is d, that should be squared there, d squared of y minus 2d of y plus 8y. That 8 just gets multiplied to that y. That's all that part means. Okay, now, what are these? Well, d of y is the same thing as y prime. And that, in our case, is 5x to the fourth. D squared of y notationally means the second derivative of y. What is the second derivative of y? From here I can see that it would be 20x cubed. Okay, so this is equal to that second derivative, which was 20x cubed, minus 2 times d of y, which is this, 2 times 5x to the fourth, or 10x to the fourth, plus 8y. Okay, 8 times x to the fifth. Okay? So this differential operator told me to do this stuff to my function, and it gave me this as a result. Okay, that notation is really, really helpful for what we're going to continue doing in this section. All right, now, in light of how we're thinking about these differential operators, I can define this as what I'm going to call the nth order differential operator for an nth order linear differential equation. So compare this to what I have up here. Okay, see if I can get them both in the same. There we go. So the coefficients an minus 1, a1, everything in between, a naught, it's all the same functions that we're seeing here. And notice the derivative, nth derivative of y, n minus 1th derivative of y, I'm using differential notation for that. Now by itself, d to the nth power, which I don't actually think is how we say that, but that's what it looks like. By itself, that's not a function. You have to think of this thing as a function that has to take some y as an input before it actually represents something useful. Okay, but this linear operator would give us this left-hand side of this dE up here if we plugged a y into this. That's the idea. Okay, so by calling this whole thing L, I can take that general nth order dE that I showed up there and just call the entire thing L of y. It's much more compact notation. L of y equals g of x, since I need a right-hand side to that thing. The L only gives me the left-hand side. The associated, or did I write that on here? No, I do that somewhere else. Okay, so that's going to be important. Now, continuing on, we're going to use that in a second. We need to define a term that's used all over the place if you've had linear algebra before. So you should be intimately familiar with this term if you've had linear algebra. If not, you should still be able to understand this. So if you have two functions, f of x and g of x, then we define a linear combination of those two functions to be another function that's equal to a sum of multiples of these. So a constant times f of x plus a constant times g of x, where c1 and c2 are just any constants. Okay, this is what we call a linear combination of these two functions here. All right, now an operator, like our differential operator up there, there's other types of operators, but an operator has a function called linearity, or we call it a linear operator if it satisfies this property right here. So basically, if I have a linear operator of a linear combination of functions like this, notice the sum here. I could split that into a sum of L of c1 of f of x plus L of c2 of g of x, and then I could take those constants and pull them outside like I have here. Okay, that's an incredibly, incredibly powerful property, even though it might not look like much at first glance. Okay, you can show without much trouble that every single nth order differential operator, like the ones we defined up here, this is that general one, is linear. It satisfies this property. We're going to show that with one example. So let's suppose that we have this differential operator, L equals d squared minus d plus 2. I want to show that that's a linear operator. So I'm going to say let f1, or let's let let's go f of x and g of x be functions. Technically, I should say that there are twice differentiable functions so that I can even make sense of this, but I'm not going to be too picky about that right now. For any constants c1 and c2, we have the following. So if I take L of a linear combination of these, c1 f of x plus c2 g of x, I don't know why I have that extra parenthesis there, g of x, like that. What is that equal to? Well, that's equal to this. d squared of my input there, c1 f of x plus c2 g of x, minus my differential operator d of c1 f of x plus c2 g of x, plus 2 times that product, c1 f of x plus c2 g of x. Barely squeezed that in there. Okay, now we know that the derivative has this linearity property. In other words, a derivative or any nth order derivative of a sum of functions is equal to the sum of their derivatives. And we also have that scalar multiple property that says that an nth order derivative of a constant times a function is just the constant times the nth derivative of that function. So what that allows me to do is say this. This is c1, that's a d squared, of f of x plus d squared, c2 comes out there, of g of x. Sorry, this is super sloppy. I didn't mean for it to be that sloppy. Minus c1 d of f of x plus, I have to subtract because this is all in parentheses. Let me go like that. Plus c2 d of g of x plus 2c1 f of x plus 2c2 g of x. Okay? Distributed the 2 in there. So I'm running out of space, which is why things are getting a little bit cramped. But basically, if I were to distribute this minus sign in, and then collect a bunch of terms, and then simplify things down a bit, this is equal to, let's see, let's collect all of my f of x's first. So this would be equal to c1 times d squared minus d plus 2 of f of x. And the reason I'm getting this is I can see that I have a c1 d squared of f of x here. I have a minus c1 d of f of x here, and I have a plus 2c1 f of x here. Using that differential operator notation, that's the same thing as this if I combine all of those terms. Okay, you can verify that. And then I also have plus c2 times, now I'm looking at the g of x term, c2 d squared, so that's going to look like this, minus c2d, after distributing that minus in, plus 2 of g of x. Okay, but these operators, the d squared minus d plus 2 that's showing up in these two places, is how I define L. So this is c1L of f of x plus c2L of g of x. Apologies for how sloppy that is. Hopefully that's readable and you're able to follow that. But this showed that I can get from here to here, which is what that linearity property is saying. Okay, so I was able to show that that differential operator was linear. We'll pick up where we left off in the next video.